Hi students, good evening. Welcome to this video session. I remain Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace. In this video session we shall discuss the motion of a projectile. We are going to look at we have about 3 cases for the motion of a projectile. In this video we shall look at case 1, the first case, and we are also going to derive the equations for some of the variables that we shall calculate. Calculations involving the motion of a projectile. The transcript of this video and the calculators for solving projectile motion problems can be found on this website, www.samdomforpeace.appspot.com. Of course, Samdom for Peace. I am Samdom for Peace. Okay, so it can be found at this website. When you go to this website, you just click on projectiles. You can also find this at any of my website, the 2 main ones, www.samuelchukwuemeka.com or www.chukwuemekasamuel.com. You can also find the link to this projectile motion videos and resources and calculators. Okay, so what is a projectile and what is a projectile motion? So some objects do not follow a straight path. Their motion is not a straight path. Of course, by now you know the straight path motion along a straight path, okay, a linear motion. Some objects do not follow a linear motion. They follow a curved path. So, but we are still going to use the Newton's laws of motion, those 3 main equations from the Newton's laws of motion to derive the parameters for the variables for this motion, for the projectile motion. So it is my understanding that, you know, from the Newton's laws of motion, those 3 equations from the Newton's laws of motion, you have the first one, V is U plus AT. The second one is S is UT plus half AT squared. And the third one is V squared is U squared plus 2AS. So this is a prerequisite knowledge. Before you talk about motion along a curved path or motion in a curved path, you should know the motion in a straight line. The 3 basic equations from the Newton's laws of motion. This is a prerequisite knowledge because we are going to use this now to derive the equations for the variables we shall do on projectile motion. So, and as I said earlier, we are going to discuss case 1. Case 1. In another video we shall look at case 2, and in another video we look at case 3. So when you understand these 3 cases, you can solve any question on projectile motion. So what is projectile motion? Projectile motion is the motion, normally it's parabolic, okay? It's along a curved path. Motion that follows a curve, and that curve is usually parabolic curve, okay? Follows the curve, parabola. From mathematics, you look at the graph of a quadratic equation is a parabola. That is the graph of a quadratic equation. So not all objects go linear. Some objects follow a curved path. So that curved path, the parabolic curved path, is what we call a projectile motion. And then that object that follows that path is a projectile. Okay, so on the first case, case 1, a good example of case 1 is a soccer player. Okay, example is a soccer player. A player playing soccer. A player, okay, playing soccer. A soccer player, football. And you know, I know soccer player. And the thing is, you know, in Nigeria we call it football. In America it has a football is not a soccer, it's not what they mean. No, we have American football. Okay, so that one is not spherical. The soccer is spherical. It's round for soccer. Yeah. So that's the thing. But you know, in Nigeria, we say soccer, we say football. But here in America, football is the American football. Soccer is now the, you know, and the US women, oh come on, they are really doing great. They are playing and winning in soccer, which is good. I played soccer. You know, when you play the soccer, you know, and I played it in Nigeria. I was a good player, if you ask me, until I stopped playing because after I had cramp. So after having cramp, I said, hey, no, I'm not going to. You know, I came back one night, one evening, after playing one evening, I came back. I could not sleep. I was cramping. So after that time, I said, I'm not playing anymore. So, but I'm a good player. I dribble. So when you play the ball, it follows a parabolic path, a curved path. So you see a player. I hope you don't laugh at me, right? So you kick the ball. You kick the ball, and then the ball, when you kick it, like let's say it's the goalkeeper. You know, let's say it's goalkeeper wants to kick the ball. You know, the goalkeeper wants now. This is not a penalty shot. No, just normally. Okay, to kick, you have the ball and you kick it. And you see the ball now travels like that. Okay, the ball travels like that. Okay? Don't laugh at me the way I'm drawing it. And until it comes to, this is the football field. Let's say this is the football field. Let's say this is the football field. So until the ball lands, until the ball lands. Yeah. Until it lands here. Okay? So you see, it is not a straight path motion. It is curved, parabolic, like a parabola. So the ball here is the projectile. This is the projectile. This is the projectile. And then the motion is the projectile motion. Motion of a projectile. The motion is the projectile motion. Okay? So we are going to look at the time to reach the maximum height. So we have maximum height here. Okay, we have maximum height. I'm gonna call this h. We have to find, and like this is the case 1, which is the main case, the default case. Case 2 we have when you're on top of a building and you throw something down. Okay. And then case 3, well, we look at or either case 2 or case 3. Case 2 when you're on top of a building and you throw something up, Then case 3 is when you just have half of this. Okay, let's say you're on top of this building and you throw something down like this. Okay, but let's focus on case 1. Let's focus on this case, the main case. Once you understand this, then the rest of the other cases, case 2 and case 3, will be easy. And we shall look at the equations for those ones as well. Okay? So, we're going to look at the maximum height. The maximum height. We want to find what is the maximum height of this ball. Then what is the time from the time you kick it to get to the maximum height? Then what is the time of flight? Time of flight is the time from this initial point when the ball is at rest. Here it is at rest. The ball at rest. Ball is at rest. Okay? It's at rest, not moving, stationary. Okay, it's stationary. 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 It's not moving. So it's at rest. Then you kick it. You kick the ball. So when it lands here and becomes at rest again. Okay, on the same level. Okay, this now is the football field, which is this is the football field. This is the football or soccer field, which is our projection plane. You can call it projection plane. Projection plane. Okay. So the time from which you kick the object, stationary object, kick it and it follows the path till when it lands and becomes stationary on the same projection plane. On the same level, projection plane. That is the time of flight. Okay. So we are looking at, we have talked about the maximum height. Maximum height. I'm going to call this h. Okay? And that is what I used in the website for this topic. Then we're going to look at the time of the projectile to reach the maximum height. The time of the projectile to reach the maximum height. The maximum height. So we're going to call this T. Let me use yellow chalk here, H. And we're going to call this small lowercase t. Then we look at now the time of flight. Time of flight. Time of flight, we shall call it uppercase T. Uppercase T, the time of flight, which is the time from the initial point the projectile was projected to the final point where the projectile is at rest on the same projection plane. Okay, on the same projection plane. That is the time of flight. Then we are going to look at the horizontal distance. So you see, we've talked about the vertical distance, maximum height. We've talked about the time to get there to the maximum height. We talked about the time of flight. So the next thing we'll talk about is the range, the horizontal distance from here to here. Okay? Range. The horizontal distance from the initial point where the projectile is at rest, stationary, to the final point on the same projection plane. On the same projection plane. We call it the range. So when I look at the range, and we call it uppercase R. Okay? And then we know we will now look at, okay, if we want the ball to, let's say we are targeting, okay? Let's say we are targeting the ball to go to the most distance. Okay, let's say we want it to go to the farthest distance. Maybe you're kind of hitting something, or you're throwing a javelin throw. Okay, let's say you want it to go to the farthest distance. We call that the maximum range, arrow max. We're gonna call it maximum range, arrow max. Number 5, maximum range. Maximum range. Let me use lowercase here. Maximum range. Okay, the farthest horizontal distance, arrow max. Arrow max. Okay, the farthest horizontal distance. Like, you know, if you kick the ball, maybe if you kick it, depending on an angle that you kick it, you can even get it, you know, here, or here, or here, or you can even kick it to get up to here. So what angle would you have to kick it if you want it to reach the farthest distance? What angle should you kick? Should you project the projectile for it to get to the farthest horizontal distance? That is the arrow max. Okay? And of course, we look at angle of projection, theta. We're going to look at the angle of projection, theta. So I come here, I write theta is the angle of projection. Theta. Angle of projection. And of course, this here is the projectile. Projectile. Angle of projection. projection theta. So number 6, angle of projection. Theta. What angle should you project it to get to the maximum range? Okay, so and like I said, we will use these 3 equations. Let me write them here. We have V equal to U plus AT to S, the distance is UT plus half AT squared, and 3, V squared is U squared plus 2AS. Alright, so let's go ahead now and derive some formulas for these parameters. Let's derive some formulas for them. Okay. So now we have when this projectile is projected, the football, which is the projectile, when you kick it, okay, so we have the vertical and horizontal. It's not a linear motion, and it's not vertical straight. Okay, so now let's consider the forces that acts on it. Okay, so I'm gonna come here and draw a Cartesian system, 2-dimensional graph, y and x. So let's consider this now. Okay, let's consider the parabola, the projectile motion, which is the parabola. So when this is projected, we have to consider this is projected at an angle. Okay, you kick the ball at an angle. There's an angle of projection. So because it's not just straight line. I mean, you didn't like kick it so that it goes straight line. You kicked it so that it goes at an angle. So we have an angle here. And as this ball keeps moving, okay, of course, anything, when we talked about linear motion, straight up, vertical motion, anything you throw up, the force of gravity acts on it to bring it down, right? Okay, so I throw this shot up, the force of gravity acts on it to bring it down. When you kick this ball now, okay, it's not vertical motion, but force of gravity is still acting on it. It's still acting on it. Now, let's say we have, and you kick the ball at an angle, and the ball travels with an initial velocity. Okay? We're now using velocity, not speed. Okay, we use velocity because it's a vector quantity. It has both the magnitude at which it travels and which direction. Both magnitude and direction. So we have here u to be the initial velocity. Let's call this the initial velocity u, which is u. This is, of course, let's refresh. From here, from these equations, v is the final velocity, u is the initial velocity, a is the acceleration, t is the time, s is the distance, displacement. Okay, let's use displacement. Okay, because displacement is vector quantity, distance is scalar quantity. So s is displacement. Okay, that is what it means from the Newton's laws of motion. So you have an initial velocity here, but then you are looking at two motions, a vertical component. We're looking at two components of this, the vertical component, and the horizontal component. So we're looking at vertical component u subscript y, and the horizontal component u subscript x. Each time the ball goes, okay, it goes with an initial velocity. However, this is not a straight line vertical motion. It's a motion at an angle. So we are going to consider, but we're not just going to use the initial velocity just as is, because this is motion at an angle, okay, the angle of projection. So we are going to consider both the vertical component of the initial velocity and the horizontal component of the initial velocity. Okay, so this is what I just said. U is the initial velocity. U is the initial velocity at which the projectile travels. It travels at a speed. I'm not going to use speed. Speed is scalar quantity. I'm going to use velocity because we are looking at both the magnitude of it and the direction, what path. So u is the initial velocity. So then u subscript y is the vertical component of the initial velocity. Vertical component of the initial velocity and then u subscript x is the horizontal component. Horizontal component of the initial velocity. Of the initial velocity. Okay, so let's now have it like this, and I'm going to erase this here, and let's derive some formulas that we will need when we start solving problems. So we have something like this, folks. We have something like this. Okay, where this is u. Now these are vectors. This is theta. Now we have the here u of y, because this is parallel to this, okay? So, and this is u of x. U subscript x and u subscript y. So this is what we have now. This is what we have. So let's find our vertical component, and this is a right triangle. Let's find the vertical component and the horizontal component of the initial velocity. So from here, you can see that sine theta is opposite SOHCAHTOA. SOHCAHTOA. From your trig, okay? From your trigonometry. You need to know trigonometry. Just some trig, okay? You need some. You need to know the. You need the knowledge of some trigonometry for this, okay? And just go to my website. Go to this website, trigonometry.appspot.com. .appspot.com. Trigonometry.appspot.com. So this, because you need the knowledge to know how I get all this, to get all these formulas. Alright, so this is opposite over hypotenuse. So this is u of y over u. U of y over u. Just some basic trig knowledge. Just some basic trig knowledge. So this implies that the vertical component of the initial velocity is u sine theta. That is u sine theta. From the same SOHCAHTOA, this is based on SOHCAHTOA. From the same SOHCAHTOA rule, we have that cos theta is adjacent over hypotenuse, u subscript x over u. So this implies that u subscript x is u cos theta. Okay? So we have found the vertical component of the initial velocity and the horizontal component of the initial velocity. Alright. Now, let's look at time to get the maximum height. Time to get the maximum height. So remember, this is the maximum height here. This here is the maximum height. This is the maximum height here. So what is the time? What is the time to get to this height? Okay. So that's our first thing. We need. Let's find time to get to maximum height. Find small t, lowercase t. Time to get to the maximum height. So here we are going to use the first, let's call this equation 1, equation 2 and equation 3. How about it? Equation 1, I'm going to call this equation 1. Equation 1, equation 2, and equation 3. Okay, so we're going to use equation 1. Let's use equation 1 for this. So V is equal to U plus AT. And the final velocity, because the ball is at rest, I know it's at rest, so you say initial velocity is 0. But that is when it's at rest. However, when you kick the ball, it travels with an initial velocity. So when the projectile is projected, the projectile moves with an initial velocity. So that means that the final velocity is 0. So V is 0. Then the projectile moves with an initial velocity. But remember, that initial velocity would be the vertical component of the initial velocity. That is the u, because of the angle of projection. So the initial velocity in this case would be the vertical component, okay, of the initial velocity. So when you project the projectile, when the projectile is projected at this angle, okay, so it moves with the initial velocity. However, because it's going back, it's projected at an angle, but that is a vertical motion, not vertical motion inclined at an angle, okay, at a projection angle. So that is why we are going to use the vertical component of the initial velocity. So this u would be u subscript y, and our u subscript y is u sine theta. Okay. Then the acceleration in this case would be the negative g. Okay, so the acceleration, when anything is, even if it's vertical motion, when something is thrown upwards, the force of gravity pulls it down. Okay, so, and even if it's projected at an angle, the force of gravity is acting on it from this initial point of projection to this maximum height, the force of gravity is working against it. Okay, so the acceleration due to gravity is working against it. That is why it's negative g. When we do the other case, okay, when we do the case whereby, for example, somebody swimming, okay, somebody, that's another case, not case one. But when we do another case whereby maybe somebody, a diver, is on the board and is diving into the pool, okay, like from here to here, then we will notice that the acceleration due to gravity is working with it. So in that case, A will be g. Okay, acceleration due to gravity would be positive g from here to from the maximum height to the final point. The acceleration due to gravity is working with the projectile. So A would be g here. From here to here, A is going to be g. However, from here to here, A will be negative g. Okay? So A is going to be negative g from the initial point to the maximum height. A is going to be negative g from the maximum height, because it is working against the projectile. It tries to pull it down. However, from here from the maximum height to the final point where the projectile wants to now land, the force of gravity is working with the projectile. So in this case, A will be g. Okay, but because we want to find the time taken to reach the maximum height, A is going to be negative g in this case. Okay, and then our t, the time, is the time taken to reach the maximum height. So this means here, from here, we now have 0 is equal to, our u is the vertical component of the initial velocity. So this is u sine theta, then plus A is minus g in this case. So minus gt, minus g times t. So this means that 0 plus gt is u sine theta. So gt is u sine theta. So t, the time taken to reach the maximum height, will be u sine theta over g. So this is the time taken to reach the maximum height. We can go ahead and write it. You can go ahead and take down the formula. Okay? So now, since we have found the time taken to reach the maximum height, we can go ahead and find the time of flight. The time of flight, find uppercase T, the time of flight. So the time of flight would be 2 times, the time of flight will be 2 times the time taken to reach the maximum height. Because as you can see here, the time of flight is the total time from the initial point of projection to the final point of landing on the same projection plane. Okay, the total time taken for the projectile to land on the final point on the same projection plane from the initial point from which it was projected. So on the same projection plane. So as you can see here, this is symmetric. Okay, so this is like half of it. So this is 2 times t. So the time of flight will be 2 times 2u sine theta over g. That is the time of flight. Remember, we are doing case 1. Okay, we can also find the time of flight another way. Okay, let's see whether we can find the time of flight another method. Okay, this is the first method to find it. Let's see if we can find it another method. The time of flight. So if we want to find another method, let's use the second equation 2. So we have here s equal to ut plus half at squared. So after the projectile lands, okay, after the projectile lands, the final point of the projectile on the same projection plane, the distance is 0. In this case, our u will still be our u is still going to be the initial component, the vertical component of the initial velocity. Okay, our u will still be the vertical component of our initial velocity, because that is because the time of flight, you have to start from the initial point up to the final point. So this is u sine theta. Our t is going to be the time of flight, uppercase T, that's our t, and our a will still be minus g, because we are considering from the initial point. Okay, we're considering from the initial point, so it will still be minus g. So this means that we now have 0 is equal to u sine theta times t. Okay, minus half gt squared. Minus half gt squared. So can we multiply everybody by the LCD? Okay, by 2. Multiply everybody by 2. Let's not deal with fractions. So we have a fraction, LCD is 2. Multiply each term by the LCD. So this is 2 times 0 is 2 ut sine theta. Okay, 2 ut sine theta minus 2 times half gt squared. So 0 is equal to 2 ut sine theta minus gt squared. Okay, so we want to solve, we have a quadratic in t. We want to solve for t. The coefficient is negative. We don't want that. Okay, so let's put everything here. So this is 0 minus 2 ut sine theta plus gt squared equal to 0. I mean, if you want to bring everything here. Okay? So we now have here, gt squared minus 2ut sine theta equal to 0. Because I don't want, negative coefficient. I don't want it. If you look at the way we solve quadratic equation. So this is quadratic in t. This is quadratic in t. And we want to find our t. It is quadratic in t, and we want to find our t. Okay, this is second method of finding this. Second method. Okay, so let's finish it. Let's finish it. So we now have gt squared minus 2ut sine theta is equal to 0. This is quadratic in t, and the third term is missing. Okay, when the third term is missing, you factor by GCF, and then you use the zero product property. So we factor by GCF t, gt minus 2u sine theta is equal to 0. So we now use the zero product property. So this means that t is equal to 0, or gt minus 2u sine theta is equal to 0. Okay? Of course, t is not going to be equal to 0. Okay, it's the time of flight. So this one you discard. You discard this, discard that. So we now have that gt is 2u sine theta. Okay, 0 plus 2u sine theta, which is 2u sine theta. So t is equal to 2u sine theta over g. So this is the second way you can find the time of flight. Okay? So we have found the time to reach the maximum height, we found it, and we found the time of flight. Okay? Right? The next thing we shall do is to find the maximum height. Let us find the maximum height. In finding the maximum height, let's see which one we can use. Let's use the number 3. Let's use number 3, equation 3, to find the maximum height. So we have v squared is equal to u squared plus 2as. Okay, so since this is from the initial point to the maximum height, okay, our v, the final velocity, is 0. Our u is the vertical component of the initial velocity, which is u subscript y, which is u sine theta. U sine theta. Our a is negative g, okay, because you're working against the gravity, acceleration due to gravity. And our s is now our h, the maximum height. Our s is now the maximum height, h. So this means that 0 squared is equal to u sine theta all squared minus 2gh. Minus 2gh. So this means that this is 0 equal to u squared sine squared theta. Okay? Minus 2gh. So bring this over here. 2gh, okay, you can say 0 plus 2gh is still 2gh. 2gh is u squared sine squared theta. So our h, maximum height, the maximum height will be u squared sine squared theta all over 2g. That is our maximum height. Okay. Our maximum height. Okay? We got that? Maximum height. Comprende? Comprenez-vous? Alright. Now let's find our range. The range. Let's find the range. The range R. With the range, let's use equation 2. Let's use equation 2. So we have S is ut plus half at squared. And in this case, our S is the R, the range. Our S is the R, the range. Our U, in this case, so the range is the horizontal distance. The horizontal distance. Okay? So we are going to use the horizontal component of the initial velocity. Okay, the initial velocity here would be the horizontal component of the initial velocity. So it is u subscript x, and that would be u cos theta. Yeah. So, you know, this horizontal component, it does not change, you know, it's the same throughout the motion. Okay, that is u cos theta. Then our A, in this case, we are looking at horizontal. In this case, we're not looking at vertical motion. We're just looking at the horizontal part. Okay, the range. So in this case, gravity does not come into play. So our A will be 0. Our A is going to be 0 in this case, because we are looking at the horizontal distance. So horizontal motion, not vertical motion. Okay? And our T will be the time of flight, because the range is the entire distance from the initial point, the total horizontal distance from the initial point to the final point, or the landing point, okay, on the same horizontal projection plane, on the same projection plane. So our T here will be the time of flight, uppercase T. So this means that we now have R will be equal to u cos theta times t, okay, times t. Actually, I should have written t first before a. That's fine. T is the time of flight. Then plus half times 0 times t squared. Okay? So our arrow, the range is u cos theta times our time of flight, which we have done, is 2u sine theta, 2u sine theta over g. Okay? Then plus 0, because half times 0, this is 0, plus 0. Okay, you see that? Plus 0. So we now see that our range RO is 2 u sine theta u cos 2 times u sine theta. So let's simplify all this, okay? 2 u squared sine theta cos theta over g. That is our range. Okay? 2u squared sine theta, because u times u is u squared, sine theta cos theta over g. Alright. If you go to trigonometry, this website, the identities, the double angle identity, because that is what we are going to use right now. Double angle identity. It's trig. The double angle identity, double angle identity. And you can, if you review this, if you really want to go into that, I think I did a lot of explanations on this website. So double angle identity is that sine 2 theta is equal to 2 sine theta cos theta. That is the double angle identity. 2 sine theta cos theta is the same thing as sine 2 theta. So here 2 sine theta cos theta is sine 2 theta. So this is equal to u squared sine 2 theta over g. And this is our range here. U squared sine 2 theta over g. That's the range. Okay? You got that? Okay. Now it's good. So it's good for you to understand the whole, how we get all this. It's good for you to understand the process. All right. We're now going to look at the maximum range and the angle of projection. If we want to get the farthest distance, the farthest horizontal distance, based on this range here, R is u squared sine 2 theta over g. We are looking at sine 2 theta now. Let's look at sine 2 theta. Sine of an angle, okay, the greatest value of the sine of an angle is 1. That's the greatest value. Of course, if you look at the unit second. So we are looking at now the greatest value of this being 1. That's what we are looking at. The greatest value of, because if this here If it's less than 1, then it won't be the farthest distance. To get the farthest distance, we're looking at this, that the side of this angle should be 1. Because that is, 1 is the highest value of the sine of any angle. Okay? 1 is the highest value. So now, we are looking at, okay, that the sine of this now, sine 2 theta, let it be 1. Okay? So in that case, arrow max would be u squared over g. That is our arrow max in that case. Because if this is not 1, then it will affect this value. So the farthest distance is u squared over g. So we got that here. We got that taken care of. But now, what will be the angle of projection to get this now? To get this, what will be the angle of projection? So sine 2 theta is equal to 1. So this means that 2 theta will be sine inverse of 1. 2 theta is sine inverse of 1. So 2 theta is 90 degrees. Okay, because sine inverse of 1 is 90 degrees. So theta would now be 90 degrees over 2. So theta would be 45 degrees. So to get the maximum range, this angle of projection should be 45 degrees. To get the maximum range, the angle of projection should be 45 degrees. Okay? I think we will stop here for today. At least you now have an idea of the formulas we have derived. Watch out for case 2 and case 3, and then more problems on solving this. Because once you understand these cases, any question they ask you, you know what case it is, and then you apply the formulas right away. Okay? Alright, thank you so much for listening, and if you have any questions, please feel free to ask. And you have a great day.